So I'm back for video number 6. I'm going to be reviewing the case borings and the cam saddle modifications today. In this one, it's always good to read a little bit of the blog here, so let's see what I've got for you today. Auditing the engine's lubrication system, we found that all the oil for both heads came through a single 5mm drilling. That drilling is 6mm on a new case. In theory, a hole that size should have provided more than enough oil, and it did, but only for the left-hand head. And then only at low RPM, which is fine for stock, blah, blah, whatever. Let's move on. Volkswagen was aware of the valve train lubrication problems and added a drilled oil channel to the rocker arms, yay, and a larger main oil gallery on later engines. And this is where it gets really important. A basic problem is that not enough oil was reaching the heads. Okay, they were doing racing, which is back in here, and what they were encountering was galling of the rocker arms. So this all started from galling of the rocker arms, and not because they were trying to throw oil at the head in order to cool the head. It's like the cooling of the head from all this extra oil spewing around is something that kind of got tacked onto the back end of it. And it seems as though that is now the primary focus that everybody's doing. It's like, I want that oil on my head. I could care less about rocker arm galling. So since we don't actually care about the rocker arm galling, let me get that out of the way really, really fast here. All right, rocker arm galling. So the bushings found that the piston pin rocker levers, and if used, cam followers, experience stop and start motion even when the engine is operating at a steady speed. The stop and start motion precludes hydrodynamic operation. Point number 2 here. Each of these joints experiences stop and start motion, so even if pressurized oil is supplied, a hydrodynamic film cannot be maintained. And this is the ultimate solution. Because the connecting rod does not provide an acceptable bearing surface, the floating pin requires the addition of a bushing to the connecting rod, which means this particular solution, which we discussed in the last video, you see these little grooves right here? These grooves are outstanding. So if you're going to go stock, use stock rocker arms, this is where you should go. Pick up a set of these. They're not terribly expensive. You do that. But the ultimate solution is to do what they did right down in here, and it's to stick a bushing in place. Your connecting rod, of course, it doesn't have any forced oil in here at all. You can see that little hole right down in there. It's got a little splash oiling. That's about it. Never galls. Never tears up. You know, the engineers used material science to deal with the problem. Rather than throwing oil at it, they just used their knowledge of material science. And of course, ultimately, what you want to do is abandon the stock stuff anyway. Go with a nice, high-performance, modern-style rocker arm that contains a nice bronze bushing down in there. We need to now talk about the oiling. And if you look in this particular drawing and you see these dashed lines down in here, incidentally, this entire drawing's out of his blog, so this is one of his. You put the drilling down here and the drilling down there, and that covers this particular piece of it called D in this drawing. The saddles, there's a little boring, gouging groove, whatever you want to call it, behind the saddles. You open those things up a little tiny bit, that would be C. Let's take a look at the drilling. So you drill down like this, and here's a drill going in like this. Well, anyway, these two drills meet somewhere back in this area, and that gives you the case borings. And then you do this particular one right here at the cam saddles. This is where the cam goes through. These are saddles. And you take that little squarish rectangular groove and you just kind of grind it out a little bit. But don't do this stuff over here. This looks like somebody's hand slipped a little tiny bit right there. So that's basically what he's talking about. Now, since he was a flying guy, and since I love to do quotes from forums at some point in these things, let me go over to the forum right now and get you a quote. So we're at the flying forum. And apparently, I didn't realize this, given that I've already reviewed a whole bunch of the Flying VW kit and assembled manufacturers for the motors. But there's this guy named Scott Kassler, Hummel Engines. Scott Kassler does not incorporate the HFix mods in his Hummel engines either. And Fly Guy Eddie says, seriously, why the hell not? And, well, yeah, if you've watched my videos, you know why the hell not. Apparently, Fly Guy Eddie doesn't watch my stuff. Fly Guy, you should be watching my stuff for sure. But we're going to have fun with it today because, you know, based on what I said last time, remember, I don't like what he's doing here. You don't want to do all the mods, but it doesn't mean that he hasn't stumbled across something that might work. You just have to give everything a fair shake. And that's what I'm here for. It's like, I don't want to bash him, but he's done some disservice to the community by putting stuff out there that is false. But it's okay. That doesn't mean I'm going to bash everything he does if there's merit. So let's see if there's merit in what he says. So here we are at the Samba, and I've got an oiling diagram. And I've used this before in some of my videos as well. What I want to look at, of course, are the moving components. I've got this stuff right here. You guys know what that is. We know what these guys are. These are my cam bearings, cam journals right there. There's not actually a camshaft installed. Kind of interesting to see it. But I don't really care too much about the rest of this stuff right here. The oil pump's going to pump its oil out. It's going to run up there, come down here. So my thought process is going to start right in this area right here. I'm going to deliver to everything over here a certain volume of oil, because this is a constant volume pump. That's what you get. You've got, what do they call these things? Positive displacements. So you turn it a certain amount, it pumps out a certain amount of oil. I'm going to assume that I have 100% oil right here. I don't really care what the pressures are. Everything's going to be kind of, relatively speaking, applied through the system. The problem is I don't know what portion of the oil goes where. I mean, I can look at this and I can look at the size of these bearings, and these bearings are huge up in here. So my guess is a whole bunch of the oil that needs to go up here to this. These are tiny little bearings, so I imagine not very much oil has to go down here to the cam journals. And who the heck knows what's going on with the lifters? So I'm going to just have my lifters are going to pick up everything else that remains. Now we have to figure out, how do we model all this stuff? So what do? Obviously, we go and we ask people, hey, what do you guys think? So we go over to the Samba. And here we are at the Samba. And I say, I'm trying to build an accurate simulation of the oil system in a stock Type 1 dual relief case. Motivation for this is the HPX mods. There's good general information on flows and pressures and other threads. However, I haven't been able to find what the breakdown of oil consumption is, specifically crank, cam, valve train assemblies, blah, blah, blah. Something like this. Crank 50%, cam 20%, and the valve train 30%. And then I've got a little message for MODOK. And let's take a look here real quick at the collective wisdom of those at the Samba. Okay, let's ask somebody else. Let's go over to Quora. I don't know if you guys have ever been over to Quora before, but here's Quora. So we go to Quora. What is the breakdown from a design standpoint of oil requiring components in the SI engine, like an LS pushrod V8? As a guess, 60% mains, 15 cam bearings, and 15 lifters, rockers, and 10 miscellaneous. Notice that my numbers for this one are different than the numbers from the other one. That's because I had begun looking up numbers myself. And I didn't want to bias anybody in particular, so these are not the actual numbers that I've come to the conclusion that I need to work with. It's just kind of a general guideline. And here's what I found out. This is the only answer that I've gotten right here, and it is of no use. So I have exhausted completely and totally the collective knowledge of every internet source that I have a certain amount of respect for. I did not go to the flying forums. I have discovered that there is actually no genuine knowledge over there that goes as far as the Samba, so why work two forums when the bulk of the knowledge is over at the Samba? So yeah, I'm sorry, flying forum guys, but yeah, there's just not enough knowledge over there. So let's continue. This is obviously a picture of the hydraulic system. So again, this is what I'm trying to model. The trick is, how do you model something like this? It's a hydraulic system, so I started looking around for hydraulic system software. And oh boy, they are like, one, the online stuff is kind of primitive, and the good stuff's like expensive. Now, I'm a KU student, so if I wanted to, I could go up to the university, and because I'm in the engineering department, kind of, I'm an EECS type, but we're all in the same building. I could go up there, and I got buddies that are into mechanical. I could go and say, hey, let's build one of these models. And I actually sent an email to one of my pals up there who's a he's an electrical guy, but we know some mechanical guys, and I'm like, hey, let's do this. And he was like, yeah, I'm actually too busy. But he gave me an idea for another package, given that he's an electrical engineer, and I'm not electrical, but I'm sort of familiar with this stuff. But anyways, the idea was, why don't we, instead of using an hydraulic package, let's use an electrical engineering package. And it turns out that there are an awful lot of parallels between flows of fluids through a system and flow of electricity through a system. So I abandoned hydraulic softwares. Not going to work, too crazy, too complicated, just not worth it for this kind of an analysis. So I went and started digging around the electrical stuff, and I came across a single package that seemed to work. I think I evaluated about 6, but I came across one package that seems to work, and let's take a look. There it is. That's the model. And but anyway, we need to take a look first at what I had to do to come up with the model. Let's take a look. So let's start with a little justification and the mindset of people who might be watching this. So here's what we get. If you happen to be a mechanic, odds are you've probably come across something that sounds like this. Let's get something straight. An oil pump does not create pressure. All it can do is produce flow. Resistance to flow is what creates pressure. All right, let's stop right there. All right, first of all, pumps put energy into the fluid. It's energy. Don't care. Past that, don't care. This, what you're looking at there, is mechanic speak. All right, energy is what an engineer does. So in order to go from this fluid system, energy, I need to go, like I say, into electricity, energy. I don't need to deal with flows and pressures and stuff. Just deal with it as energy. And when you're doing a pump, you think about the energy manifests itself not in two ways, as in flow and pressure. It has flow, as in a flow rate, gallons per minute or something like that. It's got pressure, like 40 psi at the pressure relief valve. But they also have inefficiencies, which is heat. So you've got to deal with the 3 things that pumps do. Energy transfer systems. They're never efficient. You're always going to have some kind of a waste heat process happening. Okay, research paper number 1. This guy right here happens to be a South Korean. Yeah, this dude did some pretty good stuff anyway. He's analyzing 1.6 and 2-liter motors. They are overhead cameras, so they're not push rods. Sometimes it's hard to find push rod stuff. But let's take a look at his method. So his method of doing this is the method that I am doing in my analysis. We read, further, it is calculated the pressure drop through each passage and the consumed oil flow rate of each lubricated parts. The consumed flow rate is checked whether it is in the same range of the assumed discharge flow rate or not. The results were not satisfied within a certain range of error. The procedure is to be iterated with a better adjusted value of the discharge flow rate till the value is satisfied. Finally, the discharge flow rate is decided and the pressure and flow distribution at every point and components can be contained. Now, it's not the best English in the world, but what he's got right there is exactly the process. We know that there's supposed to be a certain amount of oil going here and there. So when you build one of these systems, you have to estimate a few things. If it ends up not going where you want it to go, you go, wait a minute, I've got too much resistance here. I've got too much discharge over there. And you have to back things out a little tiny bit. But there's another piece here. Let me find it. Right, number 1, his introduction. First 2 sentences. The quality of engine lubrication depends upon how much oil is supplied and how the lubricant is fed under pressure to the lubricated components. This state of lubrication is closely related to the safe operation of an engine and the lifetime. This is crucial. This is why you do it, okay? You don't just poke the holes in the system and go, wow, I've got oil on the head. There are consequences, always a price. So that's why we model it, is to see what it costs you to shove all that oil out to the head. I have another paper here. This one happens to be from a few people that are hanging out in Sweden. And the important part up here is right up here in the abstract. This heat load has to be taken care of in some way, usually with both the water cooling and the lubrication system. Despite its name, one of the major tasks of the latter one is to draw out heat from between lubricated surfaces. In contrast to the water cooling system, which is primarily designed for cooling the cylinder block, the lubrication system is mainly required for cooling the crankshaft and piston rod bearings. This is a good paper. These guys right here actually happen to be from Iran. This particular company right here, Powertrain Company. Hey, I'll learn from anybody. I don't really care. So thanks, fellas. Anyway, they've got an abstract right here. And the important part of the abstract is, right down in this area, theoretical results are validated by a completely controlled lubrication functional test. In other words, they're going to analyze some stuff, and then they're going to compare that to an actual motor by pulling some values out of the motor. So if this motor happens to be valid, it is going to be really nice. Okay, see this guy right here? This is their diagram, basically. This is the kind of thing that I put together. You got a pump, comes up to the main gallery runs off, runs into cam bearing, I think. Main bearing rod, main bearing rod, main bearing rod, main bearing rod. Boom, something else down here, I'm not sure what this is. Cam, the cam runs up to the top, at which point we've got like rockers and something else. But anyway, it's a single overhead cam. 4 cylinders, about the right size. It is a legitimate, reasonably comparable motor. Let's see what they do. Okay, and there it is. These are the results. So what you're looking at here is the results of the mathematical analysis put into here. Some of these graphs that we passed way back up in here and stuff, those are comparisons between the mathematical computation and what they actually did. And they had a very good agreement between the computation and the experimentation. So this is a legitimate breakdown of where the oil and stuff goes. So I took that graph and I stuffed it in as the background of a graph inside the online graphing calculator called Desmos. So I take the break line, which is right through here, and I put a vertical line in. I have it scaled from 0, I don't know if you can see that little 0 down there, to 100, which sits right in here. So the 100 comes across right to the breaking point, right where the relief valve starts to pass oil out. So I'm modeling this line right here. And everything is linear down below this, so it doesn't matter. So long as you are at or below this, you get no excess capacity. So what I'm modeling is a non-excess capacity situation. So we take a look real quick at this piece, which is the main bearings down here, I believe. This chunk of stuff right here is the rods, and we look at this blue line, which is the percentage of this plus the percentage of that, gives us 64.5. Everything that I've read seems to indicate most of the oil has to go to your rods and mains. This particular analysis said 64.5. I've seen other papers where it was higher than this. I've never seen one where it was lower than what I see in this paper. This paper happens to have the best graph and the fewest accessories sticking off of it. So this one, like I said, it was the best. We've also got this one right here. We've got some lifters which go through here. We've got, let's see here, rocker arms, which I believe is this piece right here. Notice that the VW people, you don't have much rocker arm oil, so they gall, right? Well, it's the same thing here. There's very little oil going to the rocker arm. These rocker arms don't gall. So I put the oil for this much capacity, not as stock, but as the modified grooved rocker shaft, and then I backed out by a factor of 10, whatever this percentage is, to make it stock. Camshaft bearings, green to red. Let's see, green to red is about 17%. All right, I don't have that much. That's an extremely high rate. Most of the cam stuff I saw was not that high a percentage. So here we are at the actual circuit. Let's take a look at some of the things that you need to do in order to be able to get this to work. All right, right here is an oil pump. Notice I have it set up as 100 amps. I'm not concerned about oil pressures. What I'm concerned about is from a percentage standpoint. So I put 100 amps into it so I can break it down, and it basically turns into percent. What percentage goes here? What percentage goes there? So I've got it broken down into 3 different sections. Okay, up here, running here, 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 and here are the 4 main bearings. I've got the cam bearings running right down through the middle, right here. This block of 2 items right here is actually a representation for all 4 lifters on the left-hand side of the motor. This is all 4 lifters on the right-hand side of the motor. There's some minor tweaks that you might see here when you go through, let's say, a main bearing rod. I take the amperage that comes out of that particular piece. I then funnel all the amperages together to get a summation amperage. I take the left-hand side here, each individual piece, funnel it over here. This is the entire left side. I can take each individual piece to the right-hand side. I funnel them into a summation right-hand side. I then take the left and right-hand side flows, and I push them into a single amperage right there. Same thing goes for the cam bearings. Cam bearing 1, Actually, I think this is 3. So this would be cam 3, comes out. Here's cam 2, comes out. And then cam 3 comes out. And then you take the 3 flows together for the cam right here. See this guy right here? Okay, remember one of those things I said? You get your pressure, you get your volume, rates. Okay, that right there represents a heat loss. That's just an ohmage stuck out in the middle. It represents what happens when you go around the corner. So you cut a corner, it introduces turbulence. The turbulence, of course, is pissing away energy. So you got to lose energy as you do that. This one right here, this one right here, these things are a linear extraction of energy. One of those papers, it did have some stuff on how much energy is lost as you go down the main bores and up some of the channels and around corners and stuff like that. So one of those papers helped me to pick off some of these numbers. In addition to that, you've got, like, let's say that particular resistance right there. That represents coming down to the cam bearing. And when you get to the saddle is like a right-hand turn, and then it goes into the big round loop that goes around, and then it has another right-hand turn to come out to another gallop. So this is a collection of resistances that sit at this point. There's another one right there. I don't have it connected, but when you actually do the connection, which looks something like this, you do the connection, yay, everything's out of date. It alters the circuit, obviously. That'll clear. This puts it back into DC operation. And then to run the modified circuit, all you do is hit the play button. And I now have the results from a stock system that has now been overmodded with these 2 borings. I have not, however, done the cam notch expandings, which would involve modifying that one and this one. Let me see, is there anything else? Yes, there is. Notice that, let's take this one right here. Okay, that represents a main and a rod bearing. How do I know what to do with that? Well, for that, you come back over and you look at something like this. I have a single resistance, say that one right there, which is a representative of a main bearing and 2 rod bearings. The main bearing, 2 rod bearing ratios, they come from that graph. So you put those in. You then run it and then try and make this match this. And as you can see, there are a whole bunch of joined components. One of the things that I can't do with this is I cannot go beyond 25 items. Suppose I want to put another resistor in. Boop, can't do it. So you have to get clever as far as combining pieces together. That's why I've got, like, if I come over to here, I've got 2 lifters representing all the lifters on the left-hand side. But you can do that because it's symmetric. You just take the values and cut them in half. Well, after reading those papers and kind of assimilating things in my head, you kind of come to the conclusion that certain percentages need to be met. See this 66% right here? This is your main bearings. All right, I've got 12.3 something. This is the left-hand side lifters. And here's the right-hand side, 11.46% to the right-hand side. And the cam bearings ended up being approximately 10%, which is within the ballpark of what was done. I know that paper that I had the cam bearings up at like 17, but they had more cam bearings. And we've got some weird stuff with our lifters going on, so I kind of felt like I needed to put a little bit more juice into the lifters. I hate to call it juice, but hey, why not? Now comes the hard part, the boring part, and the tedious part. Yeah, you got to go look at the spreadsheet. Here we are at the spreadsheet. So I've got a number of columns here. I've got the stock right there. You put the case drilling in. I've got that column. Take the case drilling out. Do the saddle mod. You've got this column. Then put the case and the saddle mods in, plus the rocker groove, which is a good idea. Put the rocker groove on. That's good. Got that one right there. And then you do the lifter mods. So the lifter mod here is his wording. He says it's 8 times the amount of oil as stock. You've seen the videos, I hope, that I've posted about the flow of oil, based on the rockers literally in your face spewing oil, so you recognize that yes, there's a crap load of oil coming out. I've also told you that it doesn't just leak at the head; it's leaking back inside the system at the at the other end of the push rod, where you can't even see it. But the amount that's coming out at one end is going to be equal to the amount that's coming out at the other, so I've taken it and I've doubled the amount to come up with this particular column right there. So these two represent his claims, and this represents my claim. And anyway, let's take a look at stock over here. I've got 66% going to the mains. The camshaft has got 10%. The lifters are picking up 24%. The balance, left to right, is about 95%. Now, one of his claims is, oh, we got terrible balance left to right. I'm sorry, but no, it actually isn't badly balanced left to right. Now, 95% is pretty darn good. The worst lifter to the best lifter, which is going to be like an intake on the left to an exhaust on the right, you're down about 5%, 5 or 6%. So there's, it's probably measurable if you could do it, but it's not significant. So this issue of you've got terrible balance left to right is false. The balance is actually pretty darn good. It also tells you that the system was designed by a bunch of engineers who knew what they were doing, and that you probably don't want to mess with it because it actually works pretty darn well. So we do the case drilling, and let's see what the case drilling does. All right, we've lost a little bit of oil. That tells me right there the percentage of oil that I've either gone up or down relative to stock. This is for the mains. So you've taken a little bit of oil off the mains, a little bit of oil off the cam, and in order to push up the amount of oil that's going out to the lifters, your left to right balance has improved by 3.2%. You were at 95.3, you're now at 98.3. That difference between those two numbers is 3.2. And the worst lifter to the best lifter has gotten better by 2.2%. Again, whether that's measurable or not, I have no idea, but yeah, you did apparently, according to the numbers, improve the balance of the lifter and the left to right ratios. So, I mean, assuming that you don't destroy your case when making those drillings, they make a difference, but that's not very much. This would not convince me to do it. We then move over to the saddle mod. Now, the saddle mod was difficult to do because when I initially put it in, I put in a fair amount of resistance as you go around the saddle. But the thing is, the saddle's round. Okay, when you make right-hand turns, boom, boom, this causes turbulence. A nice, round, smooth thing does not really cause turbulence. So as I was putting it in, I was like, that's not right. Let me go see if I can find some information in the papers. And it's like, you find stuff in the paper and you go, they don't actually have much resistance. So that round curve that you're gouging out doesn't actually have much resistance to begin with. So the saddle mod, if you come down here and look at it on its own merit, it makes almost no difference. I'm going to show you a little picture here about why you don't want to do the saddle mod. Here's what you risk when you do the saddle mod. This is a thread over at the Samba here. This dude was putting in the mod, which I've said doesn't actually do you a lot of good, and this dude hand slipped, and he just about gouged out an entire hole right down in here. So let's continue on. Left to right total, almost no change. Let's see, the total almost didn't change very much. The left to right balance, that got a little bit better. And the lifters, worst to best, got a little bit better. You want to come, of course, look at the rocker groove, case drilling and the saddle mod. And that rocker groove does increase the amount of oil that goes to the head. So obviously, if you come down here and look at some of the changes, the oil's got to come from somewhere. So you've dropped the amount going to your mains by 4.5. The amount going to your cam is down 4.7. But of course, it results in more oil going to the head, 14.4. So, that's cool. The left to right balance has improved, 3.5%. That's nice. And the ratio between the worst and the best lifters has improved. And then, of course, you get to the lifter mod. Now, Hoover says it's by 8. So you do all the rest of this stuff, and then you get 8 times more oil to the head. But the oil is going not necessarily to the head, but it's coming out both ends of the push rod. If you count the other end of the push rod, you need to double the amount of oil that's going out. It's probably not going to be double the amount. But in my building of the 16X, I put the doubling at the push rod and not necessarily in the joint itself. So this is going to be a pretty accurate representation in this column. But here's what you got to look at. What happens when you slice open your lifter? First of all, you're going to take an awful lot of oil out of your mains. Your mains have dropped 25% of their oil. Your cam's down 26%. You have managed to shove a crap load of oil out to your lifters. Your lifters are now up 79%. It's not just your lifters. That's the lifters plus rockers. Your left to right ratio, though, has become negative. You've actually made the balance between the left and the right-hand sides of the motor worse. And the worst to best rocker has gotten significantly worse. That's now down 6%. And when you actually calculate, we're now in the 16X column, your mains are now down 38%. Your cam bearing's down about 40%. The left to right ratio is up 120.8. Sorry, lifter total is up 120. So you've more than double the amount of oil going out through your lifter. And again, it shows the balance has gotten worse. The left to right complete total off by 6%. It's gotten worse by 6. And the worst to best ratio rockers have gotten worse by 12%. Let's go up to the top and summarize. This represents the lifter grooving. 2 thumbs down. I mean, if you want to blow oil on your head, great. Look what you're doing. Look what you're doing to your mains and rods. Look at these numbers right there. You're probably thinking there's got to be something wrong with your analysis, because if you dropped your mains and rods by that much, you'd probably blow the motor up. Let's take a look at that right now as well. All right, this little paragraph right here discusses what happens physically versus analysis. It says this bearing sizing technique significantly overpredicts the oil film thickness in reciprocating piston engine bearings, typically by a factor of 2 or more. Nevertheless, it remains an important tool due to its ease of use and its effectiveness for relative comparisons. And the important thing there is, one, is this huge factor of safety, this factor of 2 or more, and then there's the ease of use. Because you remember, a long time ago, the Volkswagen guys didn't have access to really sophisticated computer analysis things, so they would have used things that were easier. So you use the easier tool, and you just know that it's going to overpredict, but you still build based on what you've analyzed. So you are surviving if you've modified your motor by slicing open your lifters. You're living on this the margin of safety that was built in by the analysis techniques that the engineers used decades ago. Coming back to the saddle mod is pointless, and you can break your motor. The case drilling, though, it doesn't hurt anything. So I bet you were thinking I'd probably say don't do the case drillings. But you know what? Hey, if you want to drill a case, look, it doesn't take much oil, and it makes a difference. For me, that's not much of a difference. I wouldn't do it. But there is an improvement in balance, and the worst to best lifter ratio does get better. Yeah, the case drilling, in a bizarre kind of fashion, it does make a reasonably decent contribution to the process, but does not have too huge a downside as long as you don't destroy your case. So I know you're still going to insist that, no, I've got to have the oil. Well, here you go. Let's take a look at the addition of the 30 millimeter oil pump into your system that you think is going to compensate for popping open your lifters. So right up in this area, you can see I put in the 115 amp pump, because if you do a positive displacement pump from 26 millimeters to 30 millimeters, it's about 15% bigger. Positive displacement means 15% more. So I'm going to pump 115% of the oil through the system, and let's take a look at where it goes. These are the results. I take these results and I'm going to put them into the spreadsheet. Alrighty, here we are at the spreadsheet. So I've added a new column in here. This is the lifter groove, X16, and the 30 millimeter oil pump. I've done the additions so that I know that I didn't type the wrong things into the system. But some of the numbers need the 100%, not the 115. So let's see what happens. Your mains are now, instead of being down 38%, they're now down about 28%. So of that 15% oil, you managed to get 10% back at your mains. These are the cams, about 40 to about 31. So you got, what is that, about 9% back on that? It's okay. But most of the oil simply goes out your push rods. You know, your oil was 120, 121 roughly. Now you're 154. The gap, the difference between left and right did not alter. So putting the oil pump in helps, but does not fix things. You know, if you just want to throw more oil at the head, yeah, it's a great way of doing it. Most of it ends up going out to the head. All right, so earlier I said I got an email from Scott Kassler. He's one of the builders of like half VWs for the flying community. I think he also does, you know, 4-cylinders as well. But anyway, these are the exact words that he sent me. The mods are good, but not really necessary for an aircraft conversion, since the aircraft runs at lower RPMs and has lower compression ratio. All right, the first piece, the mods are good. See, clearly Scott has not analyzed each individual piece. Here's a piece, here's a piece, here's a piece. Collectively, they are not good. Slicing open the lifters is just really, Stupid. And I'm going to get to stupid in a little bit later. Question for you. Okay, I got two heads. See this top head right here? Imagine that top head is 375 degrees, and this head down here is 325 degrees. And I take some oil and I throw it up on this nasty doodad, and it starts dribbling down, and eventually gets to the bottom of the rocker box, where it eventually begins to run back down the tubes. And I want to take the temperature of the oil as it's sitting here in the bottom of the rocker box. 375 degree head. So the oil temperature gets some kind of a temperature in your head now. Now, come down to this one. We do the same thing. We throw some oil up on here. This head is 325. The oil dribble, comes down, sits in the rocker box. Eventually dribbles down the tubes. But I want to measure what is the temperature of the oil sitting here. This is 375. This is 325. Maybe your oil up here is maybe 350. It's within 25 degrees. Maybe this is only 300. This oil temperature on the hotter head has hotter oil coming off of it. Colder head, colder oil. Hotter head, hotter oil. This is the wisdom of Bob Hoover. Heads ran much cooler, which means the oil coming from the heads was hotter. Here's some more Bob Hoover wisdom. Generally poor valve train lubrication. They make up a significant portion of the engine's pumping losses. Right here he's talking about rocker arms. Okay, we talked about valve train lubrication. You cannot get a hydrodynamic that's like a mixed or metal-on-metal friction that you got there. You cannot lubricate it to a point that you reduce the friction. You have to stick some kind of a bushing in there or just allow the heat to dissipate. You can't shove oil at it. Number two, significant portion of the pumping losses, false. You go back to that oil management diagram chart that I had where I said that the rocker arms socked up about 2 to 2.5%. It's 2 to 2.5% of all the oil running through the motors, what is required to do the rocker arms. That's really not much of a pumping loss. Actually, we're merely deepening holes that are already there. In doing so, we cause the holes to intersect, and when that happens, it causes the right-hand side of the engine to receive significantly more oil than it was getting before. We just went through a massive analysis where I showed you, beyond a shadow of a doubt, that it does not send it significantly more oil to the right-hand side. Remember, the stock system was basically going at about, I think it was about 94, 95% is the balance left to right. And then when you cut open, poke those holes in there, and you jump from 95% to like 98%. So, wow, whoop-de-doo, it made 3% difference. That's not significant. We extended the oil gallery for the cam follows to intersect, it's the same drillings, into the number 3, and he says, it's a big, big change. No, it wasn't a big, big change. Again, I've said this in my other videos. He's trying to give you the hard sell. Fitting an oil pump having 8 times more of the output required for lubrication alone. And trust me, the oil pump is not 8 times bigger than it needs to be. Okay? You need to take the oil, put it into the bearings, and flush out the bearing oil. Otherwise, it gets hot, and you're off to Rod City. So the oil pump it's built to capacity. It's built to design capacity. It's not 8 times. He loves the word 8. Everything's 8. All right, finally we get to his closing. Finally, there are a few who suggest I was misleading home builders because their such mods were clearly unnecessary. Yeah, they are unnecessary. However, here's what he says about me. That opinion is fairly common among builders of recreational engines. Well, I am a recreational builder, and you're probably a recreational builder, but that doesn't mean that we want to break down on the side of the road or fall out of the freaking sky. And I don't like being told by guys like Hoover, who are mechanics, who have demonstrated to me beyond the shadow of a doubt that they had no friggin' engineering. Do I sound angry? I am. When I read his stuff, it just makes me absolutely livid. He lies to you, and yet I see people just like quoting him as though this is the truth. Lies, people. Okay, let's go to the bad piece. Now, I've told you before, he doesn't understand things, but let me quote it to you from himself. It may be worth mentioning here that my formal education is very limited. I went to sea at an early age. I did not graduate from high school, nor do I hold any college degrees. He did not understand what he was doing. It's like his entire blog is like designed to impress you with like all this stuff. Do not look behind the curtain. I am the great and powerful Oz. No, he did not understand. He's a good mechanic. He's got some really good mechanicking stuff in there. Now, remember I said something about getting to stupidity? Here we go. He's got words of wisdom for us, and they are, in fact, actually rather good. Ignorance can be cured by judicious applications of valid information, but there is no cure for stupidity. Right? It would be stupid to implement these things without understanding what they do. and what cost there is. Hey, do what you want. The only one of these mods that I found would personally pop onto my motor is the rocker shaft mod. The rest of this stuff is hokey nonsense. So, good luck with your mods. I think I'm done with this.